Hello everybody, my name is Ajinkya Kulkarni and today I am here to discuss about Mohr's circle. So I shall be covering these points, that is stresses on inclined planes, principal stresses, Mohr's circle and analytical method, which is parallel to the analysis of Mohr's circle. Now let us see stresses on inclined planes. So here this element has been taken, it is a two-dimensional element and it is subjected to such type of loading. So in x direction the loading is 80 Newton per mm square and this load is tensile load. In y direction we have 50 Newton per mm square and this is compressive load. And here we have on these two planes we have 30 and 30 Newton per mm square. This is the shear stress acting on these planes. Now by the concept of complementary shear, this stress will be equal to this stress, but they will be in opposite direction to maintain equilibrium. Now let us start with the stresses on inclined planes. So first of all, let us take a 2D element. This is a 2D element and I am having forces F. Let us say F is equal to 30 Newton and this is the longitudinal axis and here I have the diameter. So phi is the diameter over here now. So phi is equal to, let us say it is 40 mm. So simply we can write normal stress is equal to sigma is equal to 30 Newton divided by pi by 4 into 40 pi by 4 into 40 square. So whatever will be the value, so we will get, so it is very simple to find. Similarly we can analyze shear stress also. The only difference is that they will be instead of perpendicular to this plane, they will be parallel to this plane and so on. But now what is the case where we have been given a general loading? So this is a case of general loading where different loads are acting simultaneously and you can see different loads are acting simultaneously and we are supposed to find out the magnitude of stresses and stresses over this inclined plane. So what will be that stress? So I am writing it over here. I am drawing the same diagram over here now. So this is the plane. So inclined plane at an angle 30 degree. This is at an angle 30 degrees. So this will be the principal stress. This will be the This will be the normal stress denoted by sigma. Then coming to this, so we are having, so this will be the shear stress tau. So our intention is to find out sigma as well as tau and the only given parameter is about that plane is the angle at which is inclined to the x-axis. So here first of all there is a method which I am going to talk about it in right now, that is called as a Mohr circle. So Mohr circle is nothing but a graphical way to analyze these stresses So before going to Mohr circle, I would also like to talk about the principal stresses, which is the second agenda. So there are some planes where only normal shear stress exists. Normal stress exists and there is no shear stress. Such planes are called as principal planes. So in two-dimensional geometry there will be at two principal planes. Let us say this is principal plane P1, this is the principal plane P2. On this there will be normal stresses tau, which will be maximum and minimum tau. So this is sigma min, this is sigma max. But there will be no shear stress. So sigma tau will be equal to 0. Or tau equal to 0. So that is the case. So even this can be plotted with the help of the Mohr circle. Then after drawing the Mohr circle, then I shall be talking about the analytical way to analytical way to deal the same problem, and we will compare the values. So right now I have explained you about the what is meant by stresses on inclined planes, what are the principal stresses. Then now coming to Mohr circle and analytical method. Let us start now. So construction of Mohr circle, it is a very interesting concept. You can find stresses on planes inclined at any angle. So there are some conventions which I shall be explaining you with the diagram. So let us start. So first of all we have to draw the horizontal axis, which is nothing but the normal stress. So values on this axis, that is the abscissa, is nothing but sigma. Sigma with the convention that there is a convention. So the tensile loading will be considered as positive and compressive will be taken as negative. So this is the origin, and I have drawn this axis, you can see. So from origin we are having this. So this value is 80 Newton per mm square. First we are going to take this plane, then we will then take this plane. So any two planes are sufficient to get the Mohr circle. So this is the 80 Newton per mm square. I am going to take it. So I will take some scale and I am plotting it like this. So I get value over here. So I get value over here as 80. Let us say this is 80. And this point is A. This is point A. Okay. So we got it. Now plane A, apart from this 80, it has also shear stress of magnitude 30. So we will consider anti-clockwise shear stress as positive and clockwise shear stress as negative. So we will take this way. So this will be 30. So I am drawing from here 30 like this. So this is anti-clockwise and this magnitude is 30. This magnitude is 30. So I am getting one point A and this is B. Now I have 50 Newtons per mm square. This is the compressive force on the plane B. So I am writing it over here now. So if this is 80 positive, so this will be 50 negative, and shear stress of magnitude 30 is also acting, but in the clockwise direction. So here I will draw it like this and I will get over here. So this is C and this point is D. So this B point, it represents, B point represents this plane and D point represents this plane. So now what has to be done? A line joining B to D is constructed. So this is the line joining B to D is constructed. So this is the reference line and we get center as E. So this ED and EB, they are equal in magnitude. So now with E as center and OB and OD as radius, so I am going to plot a circle like this. Which will pass through these points like this, D point and so on. So this is known as the Mohr circle. Now let us find out. So I will repeat the process once again. This is the horizontal axis and this one is the vertical axis. We have not taken the vertical axis into picture earlier. So this is the vertical axis which represents shear stresses tau, and this represents normal stresses sigma. So first we have taken this plane, so we have got values of 80. So we plotted O to A, this is 80, and then we have this shear stresses in clockwise direction, so that was taken to be 30. So 30 up, we got it as point number B. Then we are having this plane which is at minus 50 from O minus 50, and then even it is having shear stress of 30 Newton per mm square, but in clockwise direction. So D point comes out to be over here. So B point is nothing but this plane, and D point is nothing but this plane, and so on. Then with DB as diameter and E as center, we constructed one circle. So this is the Mohr's circle. Now all the points lying on the Mohr's circle, all the points lying on the circumference of the Mohr's circle, they depict one or another plane. Now let us see this plane 30 degree. So we have to take 2 times this value. So 30 into 2, that is 60. So 2 theta is 60. So theta over here is 30 degrees. So we have to take 2 theta. So this makes us 2 theta is equal to 60 degree. And with E as the center, we have to take E as the center. We will plot an angle of 2 theta of magnitude 60 degree. So we have to go in this fashion, that is clockwise fashion. So this is the convention when we are measuring the angle in anti-clockwise sense, like this. So from reference line you will have to go by clockwise and vice versa. So here you have, this is the reference line DB, and then I am going to take this angle as 2 theta. This is 2 theta, and this line comes to over here like this. So this point represents this plane. These points represent this plane. So there are n number of points on the circumference of circle. So they will represent n number of planes like this. They will represent n number of planes like this, and so on. So that is the peculiarity of the Mohr's circle. Now why 2 theta comes, I will tell you when I shall be writing formulas for analytical method. This can be done in analytical way also, but the cumbersome point over there is that you have to remember these long formulas. So Mohr's circle is a better tool as compared to analytical tool, I suppose. So and so now coming to this, so we got 2 theta. Now let us analyze what is meant by stresses on inclined plane, and then I will come to principal stresses. So stresses on inclined plane, you can see over here. So this is the angle this is the point we got. Let us say it is point P. So point P. Now let us draw a perpendicular from point P like this. So this is the perpendicular from point P, like this we have drawn. Now perpendicular from point P we have drawn. So let this point, this was C, this is Q. This point is Q. Now draw O to P. So O to P has to be drawn like this. So now just look over here, this dimension OQ towards the left. So this dimensions represents shear stress on that plane. Let us say this is plane P. So this represents shear stress on that plane. Let that plane be P. So OQ is equal to, so OQ we got, so that is sigma on that plane, shear stress, and by common sense we can easily judge that it is compressive in nature. It is compressive in nature. The normal stress acting over here is compressive in nature because it is towards the left of O. And this PQ, PQ, so that PQ represents the shear stress because it is parallel to the shear axis. So this represents the shear stress on that plane. So finally we are successful in finding out the magnitudes of normal stress and shear stress on the plane P. So this value you can see over here, this value is the normal stress which is compressive we got, and this is the shear stress which we got, this is the tau. So that is a way to discuss the analytical method. Now I am coming to concept of principal stresses. I already told you that there are two planes in this 2D element. There are two planes in this 2D element where only normal stress will act and there will be no shear stress. So such planes are called as principal planes, and the stresses on those planes are called as principal stresses which are normal. So there you can see, so here there are two planes. Let us say this one, we are moving from reference line. So this is the plane, this point and this point. Can you see this? This point and this point. So there is no shear stress on them, there is only principal stresses, that is the normal stresses. So this is P1 and this is P2. So they are at an angle 2 theta P. 2 theta P. This angle is 2 theta P. This angle is 2 theta P. So they are at an angle 2 theta P from the reference line. So theta P indicates the angle of principal plane over here. So 2 theta P, we have to measure it from here, from the reference line, and you have to add 180 to 2 theta P to get this force, that is principal stress. So this is one of the principal stress at an angle 2 theta P, and this one is the another one at an angle 2 theta P plus 180. So there are two principal stresses. They shall be perpendicular to each other, and they will be such that only normal stress will be acting on them and no shear stress. So that was all about principal stresses. Now finally, coming to the analytical method, I shall be writing here some formulas. So they need to be well versed. You should be well versed with those. So because in some universities a question can be asked that get the magnitudes of principal stresses both by analytical method as well as the graphical method. So you should be in the condition to attempt both of them. So now I am writing this entire now. So here we have the normal stress, that is 80 Newton per mm square. So we will write it as sigma x. This is sigma y, which is 50 Newton per mm square. This is tau xy. So this is tau xy acting on this plane. So our intention is to get value of sigma as well as value of tau. So now let us start. So we have the formula first for this plane. For this plane inclined at an angle 30. So sigma is equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2. Value is, this is going to be cos 2 theta plus tau xy sin 2 theta. This formula will give me value of sigma at this plane. Next we come to value of tau. So tau is equal to sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So that was about the plane, inclined plane. Just put these values, sigma x is 80, sigma y is 50 and so on, and get the values of this sigma and tau, and compare it with the values which we got through Mohr's circle. Next we have to find the values of principal stresses. So principal stress will occur at an angle theta p. It will occur at an angle theta p such that tan 2 theta p is equal to minus 2 tau xy upon sigma x minus sigma y. At this angle you will get two values of theta, tan 2 theta p, so that will correspond to principal stresses. Then coming to next we have principal stresses magnitude. So it is very easy, it is given by sigma x plus sigma y by 2. This is P1 comma P2. Sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. So this is the formula for principal stresses which occurs at this angle. Then we have shear stresses. So maximum shear stress can be also found out. I am drawing for your reference the Mohr circle again. So this is the circle, this is the center, and this is O, this is E. So this is this is O, this is E. So this is the principal stresses P1. OP1 is the principal stress P1. OP1 is principal stress P1 and OP2 is principal stress P2. Then maximum plane of maximum shear stress. So you can say this is the plane of maximum shear stress over here like this. Maximum shear stress which is parallel to this shear axis. So that is given by T1 comma T2 is equal to summation x minus summation y by 2 the whole square plus tau xy the whole square. So this parameter is entirely this parameter. So shear stress. Now shear stress will occur at this is the reference line. So the shear stress they will act at this line. So that is tan 2 theta s is equal to summation x sigma x minus sigma y by 2. So this is the formula for. Thus we have got the values of principal stresses, shear stresses, angles at which principal stresses and shear stresses are found, then value of sigma and value of tau at a given specific inclined planes. Now just we have to vary this parameter 30, 45, 60, any angle. Just you have to measure and put it over here. You will get the values of the. With this, I would like to conclude. Thank you.